Good morning, dear students. Welcome to Vista's Learning and online educational platform. My name is Denzil, your physics tutor for class 11. Class 11 as well as P. So this would be a session 2 of the chapter Physical World. So today, the concept that we're going to deal with is fundamental forces of nature. Now, since this is a live session, let me conduct a quick audio test and a video test. So if I'm audible to you and visible to you, kindly give a thumbs up in the comments below. So let me do a quick audio check and video check for myself. Am I good? Video quality good? So there's a thumbs up, yes. Audio quality good? Check, check, mic test. Good audio quality? Yes. All right. So let's get started with the session. So I hope you all are having an excellent day. And I believe that you would have the better day the following hours, all right? But this particular session, you would learn fascinating stuff that are related to the physical world. Now, the concept that we deal in are fundamental forces of nature. Forces. What is a force? Fundamental, meaning the most basic quantity, the most basic nature of a force. So what are forces? Let us try to ask ourselves the question and try to answer them. So what is a force? Now is it more like Star Wars, a Jedi mind trick where you say force be with you, right? So is force more of this? A force that we define by a push and pull action. Now currently the reality that we live in, forces that we deal with are certainly just the push and pull action. Even in the case of a Jedi mind trick, you still see that the forces are applied, which is either a push or a pull action on an object. Now, what are the different types of forces? Now, there are two such different types of forces, one called the contact force, the other called the non-contact force. So what are the different types of contact force? And why do we call it contact force? So let's look into the examples and then try to describe why exactly they are contact forces. Two types of contact forces that I'm going to show you is one muscular force, the other frictional force. Muscular force, meaning when you provide certain energy to an object. So you push an object. When you push an object, what you're doing is you're applying force on an object. Since it requires an interaction with an object, which means you need to have contact with the object in order to apply force. So this contact on an object to apply force, the forces are termed as contact forces. And two such forces, one muscular, the other frictional force. Have you ever wondered why frictional force is a contact force? Let's take an example of a ball, rolling a ball on the floor. So when you take a ball and roll it on the floor, what you notice that ball will eventually come to a halt. Why doesn't the ball roll forever? Why does it come to a halt? That's because there's an opposing force that is acting onto a ball, which is a frictional force. And frictional force only comes into picture when there is a contact with the surface. So why exactly? So different surfaces have different friction, provides different frictional forces. Certainly you do, yes. Different surfaces like rough surfaces and smooth surfaces. When you have to go sliding onto a surface, which you have done in your childhood days, so some of you remember sliding on the floor. So sometimes when the floor is not that slippery, what you do is you try to put talcum powder on the floor and then you try to slide on the floor. Rather, you also use talcum powder on a carom board. So when the board becomes rough, what you use is a little bit of talcum powder. And why you use the powder, there's a talcum powder and a carom board powder. I think you use a carom board powder for a carom board, right? So you use this powder on a board or on a surface, and why you use that is to reduce the frictional force. So frictional force only comes into picture when there is contact between two surfaces. Now, since these are contact forces, what are a few examples of non-contact forces? And why do we call it non-contact forces? Is because they do not interact with an object. There's a force applied on an object even though there is no contact between them. So what are the other examples of non-contact forces? One is a gravitational force. So any object that is freely let go, when it is let go, what happens is the object falls to the ground. Now you don't see anyone pushing the object to the ground, but it takes place which is automatic by itself. Where objects fall to the ground, it's because of what is known as a gravitational force. And these type of forces, this particular force is an example of a non-contact force. Few other examples: electromagnetic force, electromagnetic. Now these are two different entities what you see. Electricity, magnetism, the two different fields. And how is that two different fields are put together in one as an electromagnetic force? Now for this we have also discussed in the last session where unifying a theory. We discussed one particular unification where Newton unified the heavens above and the earth, unifying the two fields, that is space, a gravitational force that exists in space, the same gravitational force that exists here on earth. So unifying the heaven and the earth. Now there's also unification of these two, which is electricity and magnetism. Well, electricity and magnetism, there are a lot of scientists who have dedicated their life for unification, starting with Michael Faraday. Michael Faraday provided an experimental proof that electricity and magnetism are correlated, but it was not theoretically set. It was only done by James Clerk Maxwell. Maxwell unified it mathematically and so forth and so on. Now today we have, due to the unification of these two forces, we have technology. The reason why I'm able to communicate to you is by these forces which are actually acting. So certainly you must have, you will be learning about electromagnetic wave and so on, but an electromagnetic force is where it starts with. The forces that acts between charges and magnets, so that correlate. So another is an example of a strong force. Strong forces, we'll have a look at what are these strong forces in the further section. So in the next section, we will see what are the various strong forces and also what are the various weak forces. So these four are the primary non-contact forces, forces that do not interact with any object. They have an effect on the object, but they do not interact. There is no contact. So let us start with what are four fundamental non-contact forces. So a quick recap, what are they? One is a gravitational force. Two is electromagnetic force. Three, you have strong force, and four, you have weak forces. So let's get started with, so we have gravitational force, electromagnetic force, strong nuclear force, and weak nuclear force. So what I want you to look at here is the term which is used, nuclear, strong nuclear force. This is something that we shall discuss in further section. Like I told you, that we'll be discussing about weak forces, strong forces, but weak forces and strong forces that exist within a nucleus. Nucleus of what? Is it a nucleus of a cell? Nucleus of an atom? Well, stay tuned. We will have a look at it. All right. So let's start with the first fundamental force of nature, which is gravitational force. Let's take the case of an apple, which is here towards your right hand side, which is my left hand side. Now, this apple, now currently I'm holding this apple, which is certain height above the ground. But when I let go of the apple, what happens? Is that the apple falls to the ground. Now, did anyone push the apple below? Did anyone apply force below towards the earth? Well, that's because of earth itself, which is very massive. Well, compared to us, it's very massive. It is producing its own gravitational force, which is towards the center of the earth. So any object that is let go, it will fall towards the center of the earth. So this apple, which is currently dropped below, there was no contact, there was no force that was in contact with the apple, but there was a force acting on the apple, and the effect, what you observed, is the stationary apple started moving. So that is the effect of a force. Now the other effects of force you must have learned in your lower standards. There are 5 different effects of force. Can you name those 5 different effects of forces? 1, it can move a stationary object, which means at rest, it can set it to motion. This is one effect of force. So let me write it here. Effects of force. 1 is that stationary objects, which is stationary, starts moving because of force. 2, object which is already moving can come to a halt by applying a force. An example, nowadays you watch cricket matches on television, and especially when it comes to your favorite team who are fielding and they catch the ball. So when they catch the ball, which is already in motion, and when they catch it, what they're doing is they're applying the opposing force in order to catch the ball. They're applying opposing force to catch a ball. They're changing a state of motion to a state of rest. Okay. Third effect of force is that it can change the direction. Can you give me one example where such effect of force is observed? Let's take the same case of a cricket match. When your favorite team is now batting and they need to whack a 6. So what do? The incoming ball, its direction is changed by applying a force by a bat. Okay? Direction of the ball is changed by applying force using a bat. So change in direction is one of the effects of force. Fourth, you can also change the shape of an object by applying a force. This is quite interesting. How can you change the shape of an object? Can you give me one example where the shape of an object changes when a force is applied? Let's talk about your breakfast. Now, some of you might have had chapati in the morning. Now, the chapati is prepared using a dough which is circular in shape. Now, you take a rolling pin, and then you flatten the dough by applying a force. So, you're flattening a dough, which means the shape of the dough has now been changed. Therefore, it is one of the, again, effects of force. The other example is pottery. When a potter has to make a pot, he takes a clay and he turns the clay, shapes the clay into a desired shape he likes. So this is another effect of force, which is change in shape. And one last effect of force. Like I told you, there are 5 effects of force. Now that we have done 4, can you identify the 5th one? Because these effects of force were discussed in the lower classes. If I'm not mistaken, should be in your NCERT class 8. So can you guess what would be the 5th one? Change in the velocity. Change in velocity of the object. Let's say cycling. So when you're going cycling, let's say you're moving at a constant speed and now you want to increase the speed. So what do? You pedal even harder. So when you pedal even harder, what happens to your cycle speed? Changes. So that is another effect of force. By, by applying a force on an object, it could also change the velocity of the object. So these are the 5 different effects of force. Now, gravitational force can also exhibit those 5 different forces because it's a force which is a non-contact force, but it can exhibit those 5 different on an object. Now, here's a popular question by Sir Isaac Newton when he observed this apple falling to the ground. In the late evening, when he sat under an apple tree, he watches an apple fall to the ground. Since it's a late evening, you also have a little bit of celestial stars that will be visible, like commonly that we call as the evening star, and also a moon. There was a sight of moon. So he observes an apple that falls to the ground, and then he looks at the moon. And he asked this very famous question. Therefore, even today, we appreciate Sir Isaac Newton. It's not just what he has formulated, we appreciate because of his popular question. And this is his famous question. If an apple falls to the ground, then why doesn't the moon fall to earth? Well, this was a very interesting question. An apple that falls to the ground, but you see a moon does not fall to the earth. There's gravity acting on the moon as well. So moon's gravity that is acting on earth, because you see the tides. Tides in the ocean is because of the moon. Now if such case happens, why doesn't the moon fall to the ground? I leave that question up to you. You go ahead, try to conduct a research just like what Newton did. I want you to go and explore. All right? So let's move on to the next type of force, which is an electromagnetic force. Now, like I told you, electricity and magnetism were 2 different fields. Now, when it comes to a magnetic effect, what you notice, a magnet attracts magnetic materials such as metals. Now, for a magnet, you have a north pole and you have a south pole. Now, the few properties of a magnet that you might have learned, there's some, you might have also experimented with magnet. You might have taken 2 magnets, brought it close to each other. You might see that it may attract on one end, but if you reverse, if you turn the magnet and then you try to attract it one more time, it does not. It repels each other. So those are the few properties of magnet which you will be learning in later stages. Not to worry, we will be going through that. All right. So magnets have the ability to attract magnetic material. Now, in case of charges, here's a small clip where all you have to do is take a comb and try to rub it against your, run it through your dry hair, not your wet hair. Don't take a shower and come and then try to rub it through, all right? On your dry hair, take a comb, okay, rub it, and then bring it close to bits of paper. You might have tried this in your lower classes, but then what is more fascinating is these bits of paper get attracted to the comb. How does comb attract bits of paper? Comb is not a magnet. Bits of paper are not the magnetic material, but how are the two? How is bits of paper getting attracted to the comb? Well, I'll answer to the question so that I'll remove, we'll sort it out and get rid of the confusion that we have. Now, when it comes to using a bits of paper, these bits of paper have equal number of charges. Now, can you specify what are the different types of charges that you're aware of? There's one positive charge, there's a negative charge. When a positive and a negative charge are equal in number, then you have neutral charge. So when it comes to our bits of paper, they are neutral in charge. But within them, there are set of positive and negative charges. So the equal number of positive and negative charge. Now when you take a comb and when you run it through your hair, what is happening is there are few charges, free charges in your hair, and those get transferred to the comb. So a comb is now charged with negative charges, electrons. Now, one of the property of charges, negative charges attract the positive charge, and the negative charges repel the other negative charges. Therefore, bits of paper contain both the charges, negative as well as positive. So what happens is all the positive charges get aligned in one direction, all the negative charges will get repelled in the other direction. Due to the charge separation that it takes place, these positive charges will try to lift the paper up is because it causes a force. So there's a force that is acting due to these charges. When you have a negative charge, positive charge, they come together because there's a force applied on each other. This is why you see paper that gets attracted to a comb, hairbrush, right? So now that we have unified the two different theories such as magnetism as well as electricity as one form as an electromagnetic force, what are the benefits? Why are we using it? Now there's one reason I can give you is in case of a turbine, in case of a windmill where you have to generate electricity. The places where there's electricity generated most of all, you use an electromagnetic force in order to produce electricity. So you're making electricity out of magnetism, which again will be discussed. It is part of your syllabus. We will be discussing that. So those are usually done by this huge mechanism called the turbines. Okay, due to the rotation of the turbines, it generates electricity. So this is a second type of force called electromagnetic force. Moving on to the third, which is strong nuclear force. Now I specified which nucleus are we talking about. Now the nucleus under discussion is the nucleus of an atom. Now here is a clip where you observe that they are there's something that is whizzing around the center. These things that are whizzing around the center are what are called electrons. So let me specify that. Okay, electrons. So more about the charges, about electrons property will be discussed. You have a syllabus, it is a part of your syllabus where what is the charge of an electron and what is its property, what's its mass, and how much is the value of its charge. All those are part of your syllabus, and we will discuss them in later stages. But now, those particles which are whizzing around or which are moving around the center is what are called electrons. And this which is located at the center, now you see those three balls which are located at the center, this is called the nucleus. Okay. Now nucleus is composed of nucleons, particularly nucleons meaning each individual particle are called nucleons. Nucleons are composed of two types which are protons and neutrons. So nucleus, inside nucleus you have neutrons and protons. Interesting. So you have electrons that move around the orbit in a particular orbit, and then at the center you have nucleus, and nucleus is composed of neutrons and protons. So this is how a rough structure of an atom, how an atom will look like. Now, where does the strong nuclear force come into picture? Where is it located? Strong nuclear forces, forces that exist between the nucleus or nucleons. So forces that exist inside the nucleus. So what are these forces? Where exactly inside the nucleus? Now, neutrons or protons are present within the nucleus. So they're held together with some forces. A neutron and a proton are held together with some force. Now that force is what we call as a strong nuclear force. Okay, so I hope I've made that easy for you. Protons, neutrons are held together by a very strong force, which is called strong nuclear force. Now moving on to the next is weak nuclear forces. Now nuclear, again, nucleus of an atom. Now in this case, we take a particular example of a neutron. Now we'll observe that there are two nucleons present, one which is called neutron, the other which is called proton. Now what happens is neutron decays. Now how you observe that objects decompose, we have nucleons as well which decays, more like a decomposition. So it decays to give an electron and also a particle that's called an antineutrino. So these two particles are emitted, neutrons, also called, this process is also called as a beta decay. Okay, you will learn more about this, not to worry, it's just a general introduction that I'm giving, not to worry. We will be discussing this one more time in depth rather. So by beta decay, you have an electron that's emitted as well as an antineutrino. And after it goes through a decay, what you get in turn is a proton. So neutron can turn into a proton by a process which is called a beta decay. So here I've used a Greek letter which is beta. Okay. You will be learning few Greek letters in this course in physics. We use Greek letters mostly. That's because we want to differentiate them from the other normal variables that you have learned, which is X, Y, Z in case of mathematics, A, B, C's. So we want to keep it more distinct and more detailed or comprehensive to make a comprehensive study. So beta. So we are using Greek letters in order to represent few things. Okay. All right. And finally, nature of physical laws. Nature follows certain physical laws. What are these physical laws? Now, when it comes to force, when you apply certain force, let's say 100 newtons of force that is applied in an object, or if you're weighing about 30, 40, 50, 60 kg, that means it is actually your weight, but then if you convert it to your mass, then you, let's say if your mass, which is about 20, 30 kgs, then you say you produce, which is of 3 kg force or 3, 4 kg forces. That's because once you can, or 30 to 40 kg forces, since I'm saying 30, 40. So you'll be producing, which is 30 or 40 kg force. Now, when you apply force on an object as 30 or 40 kg force, or which you are 30 or 40 kg force, what you notice is these forces that are applied, they cannot be taken back in return. They cannot be converted in any form. Once the force is applied on an object, it is given, it is lost. Now, there are some physical quantities which cannot be created, not be destroyed. Which are those physical quantities? One is a law of conservation of energy. Energy is one such physical quantity. It is the most important property of important physical quantity in physics. Now, there's so many things that are happening in the universe at the moment. You see the sun is generating light. It is giving you light all because there is a nuclear reaction that is taking place within the sun. Almost everything that you look around you, there's a whole energy process that's taking place. But one thing you realize is all this energy is conserved within the universe. The energy that is created and the energy that is destroyed, that does not take place. It is only being transformed from one form to another. An example, when you take an electric bulb, when electricity is passed through the bulb, an electrical energy is converted into heat energy first, and the heat energy is then converted into light energy. So you see a transformation of energy from one form to another, but then energy is not created nor destroyed. It's only converted from one form to another. Then you may ask the question as to where is the beginning for an electrical energy? Where does it start? Well, that's a question for you. give me the various sources of electrical energy. Where can electricity be harnessed from? Okay, various sources of electrical energy. So when it comes to energy, it has this conservation law where it cannot be created nor be destroyed. Let's have a quick look at this example of a roller coaster ride. Now, when the roller coaster is at the top, the very peak, potential energy, so when it comes back, so it's going on a loop the loop and then it comes back to its same position, there potential energy is maximum, but as the object moves down, as the roller coaster moves down and goes loop the loop, you notice that kinetic energy increases. So there's a change in energy from a potential energy to kinetic energy, and the change keeps occurring as the object is set into motion or if it is stationary at a given height above the ground. But also notice this particular factor, which is total energy. As the roller coaster goes round, it remains the same. It does not vary. Though these two are changing, total energy remains the same throughout the journey. So this brings us to an important, which is conservation of energy. Now you may ask the question, is there a proof to show me that this conservation energy exists? Now, it is wrong to ask for a proof when it comes to conservation energy. Then you may say that you have learnt in your lower class that there's one proof, which is half mv square plus mgh equals to constant. Isn't this a proof? No. This is not a proof to show that the energy is conserved. This is a verification to show that the energy is conserved. Okay, so there's a big difference between proving and verifying. So you cannot prove that there's conservation of energy. Rather, you can only verify using this following relation, which is half mv square plus mgh equals to a constant. So, and one last again. So what are the various conservational laws that we have? For now, I would provide you with conservation of energy, conservation of linear momentum, especially when you're playing a carom board. Then when you hit what, I don't know what they call the white. So when you hit the white circular disc and that goes and hits the other disc, so what happens? The momentum is transferred, but the momentum is not lost in the process. Therefore, linear momentum is also conserved. Conservation of angular momentum, there's also conservation of mass. Interesting fact about conservation of mass, which was actually understood by Einstein's mass energy relation, where we note down where E equals to mc square, a very popular relation. E equals to mc square, all right, where energy equals to mass times the speed of light square. So this relation shows you how energy is related to mass. So any mass can be converted into energy, or any energy can do the vice versa. So there are a couple of experiments where a given energy can also be converted into mass, especially in a bubble chamber experiment. Maybe you can have a look at it. A hydrogen bubble chamber experiment. Okay, hydrogen bubble chamber. Okay, in a hydrogen bubble chamber experiment, what they do is they pass light into a chamber which consists of hydrogen bubbles, and that light, which is nothing but energy, gets split into two different particles, yes, which have certain mass in them. So energy can be converted to mass and the vice versa process. And that is where the conservation of mass is truly understood, is by using Einstein's mass energy relation. Okay, so this is rest mass, which is m naught. Okay, so that I'll mention. And that is all for today. If you've liked the video, then make sure you give a thumbs up, subscribe, and click on this bell notification. Do fail to stay tuned by visiting us www.we-learning.in. So share this with your family and friends. There are classes that are ranging from class 1 to all the way class 12, various other subjects, different subjects. So go ahead, have a look at it. I shall see you all in the next session. In the next session, we'll start with a brand new chapter. So take care, everyone. Have a nice day, and thank you, and good luck, and I'll see you soon. Bye-bye.